So, fortunately, I think it's not necessary to introduce the notion of maps again. Mire has already done it. So here, but the only difference between her maps and the maps I'm considering here is that they are all rooted by an edge. So, no. But, it's not bipolar. Okay, it's just so there you have a root vertex and a root edge. So here, so this gives with a direction. So this is the first vertex and the second vertex of this root edge, and so on. So it's embedded. So it's a graph that is embedded into the plane or to the surface of the two-sphere. In the final part of the talk, I will also consider more general maps on surfaces, but let's start with planar maps. And as already mentioned by Mireille, so this the story goes back to Tat, to the 60s, and Tat enumerated the number of maps with n edges, a very nice formula, and nowadays we understand why he obtained these nice formulas. So it was around the development of the so-called quadratic method, which this does not explain the kind of nice formulas. But I want to point out that from this explicit formula you get a very nice asymptotic, so that 12 to the n is an exponential part, but what's most interesting is the sub-exponential part, which is n to minus 5/2. That follows directly from this explicit representation. But the topic of the talk is not only the asymptotics of the number of maps, but more precisely the degrees or the distribution of the degrees in planar maps. So the first thing that is known for a very long time is that if you consider the degree of the root, so this is degree of the root vertex here, then it's well known that this the probability that this root degree has the degree of this root is k, that stabilizes, you get a limiting probability for every k, and it is positive for every k. A different question is to look at a randomly chosen vertex, so not to the root, but to a random chosen vertex. And the statistics is a little bit biased because of the root edge. So but anyway, you also get a limiting probability. So if you consider the probability that a random vertex has a degree k, then again stabilized to a limiting probability, positive probability. And both probabilities are related but not the same. And of course, this probability is related to the expected number of vertices of degree k. So this is then proportional to the number of edges, or it should be here because we are counting vertices, so it's not the same concept. It's just it's related to this concept by a fixed value v, which is just the asymptotic proportion between the number of edges and vertices. But anyway, from this you get that the expected number of vertices of degree k is proportional to n with a fixed proportion mu k, which is positive for every k. So it turned out that it's not an easy question to consider a more precise statistics on the number of vertices of degree k in a random planar map with n edges. But a few years ago, together with Panagito, we extended the quadratic method, which is more or less a counting method, to an analytic version. So we perturbate it a little, and could show that the analytic structure was very similar with this perturbation. And this perturbation comes from if we want to also count the number of vertices of a given degree. Anyway, we could show that we actually have a central limit theorem as expected for the number of vertices of degree k. So the expected value is proportional as before. Also the variance is proportional to the number of edges, and we have a central limit theorem. Now, it's also interesting to consider different classes of random maps, and here is an incomplete list of some classes of maps. So, for example, Eulerian maps or three-connected maps, loopless, two-connected, bipartite, and there are many others. And in all cases, we have the same kind of asymptotic, so an exponential part, a sub-exponential part, which exponent -5/2. And it seems that this is a universal property, and there are many explanations for this in all these cases. There are bijection to trees and so on. I will also consider a bijection to tree a little bit later. What I want to show you first, so the first theorem, is that to extend this universal property to maps with given degree restrictions. So for example, if I consider Eulerian maps, which this precisely means that all degrees are even. Okay, you have an Eulerian path if and only if all degrees are even. And this is a generalization of this, so I consider an arbitrary subset of the positive integers, and I consider only those maps where all vertex degrees are contained in omega. So this could be, for example, the even integers, then you get the Eulerian maps, or by duality the bipartite maps. Or you can, if you just consider a singleton 4, you get 4 regular maps, or by duality quadrangulations or triangulations, 3 regular maps. But you could also consider the prime number. So you consider only maps where all degrees are primes. And the result that we have here is that this universality, so this universal property here, is also valid for these kinds of maps. So for every arbitrary subset of integers, you get the same kind of asymptotics with some constant sub-exponential part n to -5/2 times an exponential part. Well, as mentioned before, there is a dual version of the theorem, so you can always replace degree by phase valency. So if you consider the dual graph, then vertex degree translate to phase valencies. So that you could say this, the same theorem is the following. If you just consider planar maps where all phase valencies are contained in this set omega, then you get the same, of course it's the same number, you get the same asymptotics. And the second remark is that if we restrict on Eulerian maps, just Eulerian maps, and consider only a subset of even integers. So then this theorem is not new, it was proved by Bender and Canfield. But what is new is it is not only true for Eulerian maps, but it's true for any kind of maps, where omega can be an arbitrary subset, not only a subset of even integers. Okay. And the second theorem refines the theorem that I mentioned before together with Panagito. So again, I consider the number of vertices of degree k, but not in general maps, but now in these maps M omega, where omega is an arbitrary set of maps, arbitrary subset of the positive integer. Then you again have that the expected value and variance are linear in n, where n is the number of edges. And you can prove a very general version of a central limit theorem. You can put all these random variables together. You get an possibly infinite vector of random variables. And if you normalize, so you take the difference between this vector and its expected value and scale by the square root n, then this random vector converges weakly to a centered Gaussian random variable in L2. And again, by duality, the same theorem holds if we replace degree by phase valency. So this now it is essential that you replace it at every step. So if I consider now omega, I consider M omega to be the class of maps where all phase valencies are contained in omega, and x and k denotes the number of phases of valency k, and then you get the same theorem. So you have to place it in both cases. You cannot, it's not possible, at least at the moment, to change just one part from vertex to phase. Okay, so maybe I should explain quickly what does this notion really mean. So we have weak convergence of random variables that are Banach space valued. In this here in our setting it's just L2, and weakly can be rephrased in terms of weak convergence on of all continuous functionals. So you just here you have one-dimensional random variables, and secondly the set of laws of these random variables has to be tight. So this is Bohrov's theorem in this context. It applies. And Gaussian means that all continuous functionals of these random variables are Gaussian and centered. So I did not mention it. Centered means that the mean of this is 0. So in the theorem with Panagito, we used the quadratic method. But this quadratic method is not very flexible. So it has some flexibility, but it is very complicated if you consider more than 1 degree. And it seems to be impossible to consider several all degrees at the same kind. Yes?
Can you explain what's the quadratic method?
The quadratic method is a method to solve a functional equation of a generating function where you have a so-called catalytic variable. So I hope I can recall it correctly. So you have a generating function in 2 variables, m of c and u, and you get a relation of this function similar as before, as in the talk of Mireille, where you have some function of c and u, and you have also now this function here and m of c1, and q is, say, a quadratic in this I think in m, and then there is a general method how you can solve this kind of equations. So of course it's very easy. So the problem, if you put u to 1, it seems that you should get an equation for this function, and then you can iterate. Unfortunately, in this context of map enumeration, if you put u to 1, you don't get anything but 0 equals 0, or something like this. So you have the trick is more or less that you put u to a function u of c, and then because of the quadratic dependence on the right hand side, you can also use the derivative, and you get 2 equations, and then you can solve this functional equation. This is the quadratic method. Okay, is the question answered, at least partly? Was it right? No, so she's the real expert of the quadratic method. And not only of that. Well, I want to next come to mobiles. Mobiles are more or less trees. But the important thing of mobiles is that they are closely related to planar maps. And they are quite easy to count. And actually, the counting of mobiles, that is much more easy, explains the nice formula that has given by Tat, where he used different methods similar to this method. I tried to explain with the quadratic method. Okay, so but here I want to exploit this mobile also with respect to the degrees. So I have to be slightly more precise. But this is not new what I present here, but this is just a collection of things that we really need. So what is a mobile? A mobile is a planar tree with two kinds of vertices. So this is an example. So it's a tree. It looks strange, but this comes from an example that comes later. So it is a tree where you have two kinds of vertices, white and black. But there are no white edges. So there might be black edges, of course white edges, but a white vertex has only black neighbors. And the black vertices have also something that are called legs or flags or whatever. So these are a kind of half edges or maybe even shorter edges with some error. So, and there is a condition that the number of legs that you have at the black vertex is precisely the number of white neighbors. So here you have two legs. And be careful, so if I put this leg here to this corner, then it's a different mobile because it's planar. So it's always embedded into the plane. So you have to be careful to put these legs. And of course, you also have to be careful to put it into the plane as it is. So this is a mobile. And well, there are some special cases. A bipartite mobile is a mobile where you have no black edges. So this is not a bipartite mobile because you have a black edge. And another notion is the degree of a black vertex. A degree of a black vertex is the number of half edges, so the number of plus the number of legs that are attached to it. So for example, the degree of this black vertex is 1, 2, 3, so the number of half edges attached to it, so the usual degree plus the number of legs. So the degree of this vertex is 5. So we don't care about the degrees of the white vertex. And then we can also root a mobile with an edge by just putting an oriented edge somewhere. So the reason why we will use this root is that then it will be possible to count these objects. And there is, as I mentioned before, there is a very well-known relation between these mobiles and maps. And this has a long history, so I hope I did not forget any name, an important name here in this series. So the mobiles itself were invented, I think, by Potier, Di Francesco, and Gitter, but they have been extended and so on. But there are several variants of these kinds of trees, and there is the Scheffer bijection is also related to that. So what is the relation? So actually there is a bijection between mobiles and pointed planar maps. So what is a pointed planar map? This is a planar map where one vertex is pointed, so it's not rooted. So there will be a rooted version is this. So where I root an edge. So this is a rooted and pointed map. Actually, we will use this. And there are several relations between these mobiles and pointed planar maps. So the white vertices of the mobile correspond to the vertices of the planar map. So here's the corresponding mobile. So the white vertices correspond to the vertices of the map. Only the pointed vertex disappears in the bijection, but can be recovered, of course. And what is the other relation? So the black vertices of the mobile correspond to the faces of the map. So we have the black vertices. So, and I will explain the bijection a little, then they correspond to the faces. So this is the outer face here, and this vertex corresponds to this face, and so on. And what is important for us, the degrees of the black vertices, in this sense that I count also the legs, corresponds to the face valences of the map. So, for example, here I have this vertex of degree 5. This corresponds to this face that has valency 5. Okay, and this bijection, so the number of edges stays the same. So the number of edges of this map is precisely the number of edges of this mobile, and we can root it. So if we root a mobile, we get a rooted pointed map on the other side, and bipartite mobiles correspond to bipartite maps. Bipartite is precisely the same condition that all face valences are even. Okay, so this is the theorem, the bijection. So how does the projection runs? So the first thing is that you consider a pointed map, and the next step is that you orient the edges of the map. So these orientations are not present from the beginning, but when after you point a vertex, then you just direct the edges away from the pointed vertex. Of course, there are some edges that get no direction because both endpoints have the same distance to the pointed vertex. So you have two different kind of edges, oriented edges and non-oriented edges. The next step is that at every face you put a black vertex, and then you use the following rule. So now the edges will be dashed of the original map, and if you have a non-oriented edge, you put an edge between the two black vertices corresponding to the two neighboring faces. So here is an example. So if I have here this face and this face, so this is non-oriented, so I connect these two black vertices here. And if they are oriented, then I do apply a different rule. So I connect this white vertex with the black vertex, this represents the face, and I just put a leg to the other black vertex corresponding to the other face. And be careful, the orientation is important where you have to put the edge and where you have to put the flag. And if you apply this to all these edges, then you get this picture. And at this moment, you can delete all these dashed edges, so which are precisely the edges of the original map, and you can also remove the pointed vertex, and what remains is a mobile. And this is a bijection. And this is also a bijection if I take a rooted version, because the root edge can be easily related to a root of the corresponding mobile. So that's the bijection. So, and in order to get statistics on the mobile, on the map, I just have to look at statistics. For example, statistics on the root, on the degrees of the black vertices correspond to statistics on the valences of the faces of the map. So this is not new. This is just a recollection of things. And also, this counting lemma is not new, so this is very well known in this field. So now I want to count things. So what I do is I consider a formal generating function that where I count the number of vertices, edges, faces of valency 2, faces of valency 4, and so on and so forth. So I should maybe note that now for the proof I used a face valency point of view. And by duality I can rephrase it back to vertex degrees. So this is a formal power series in infinitely many variables, and this by this bijection I can relate the corresponding counting generating function of mobiles. So this is the generating function of a very specific kind of mobile. This is this kind of mobiles where I have a root edge starting at a white vertex. So, and I put also an additional edge here. It's just sometimes this is called planted tree. So, and if I put this root edge here, then I have a very nice recursive structure. So this is now a root. This gives me a first descendant and a second and a third. So I have a sequence of descendants, and what is coming next are again mobile. So I have a recursive structure of again rooted mobile. So I can always put here a root. I'm sorry to put a root, and this gives rise to this recursive relation. I come back to this question. And the bijection between mobiles and maps now gives a relation between the generating function of these mobiles that have a very nice recursive description to the generating function of maps. So I have to solve this equation. It's an implicit equation. So this uniquely defines a power series in these infinitely many variables, and then the generating function of the corresponding maps is given by this relation. So here you see a derivative with respect to t. So what is m? M is the generating function for the rooted maps. So if I take the derivative with respect to t, this is just the rooted and pointed version. So this is the pointing operation. And this is the pointed rooted maps are then related to rooted mobiles. This is the relation. Well, this picture gives the recursive structure. So, and this can be also rephrased in this form, which is equivalent to the previous. So this is the same as that, just an algebraic transformation. So this is, but this is, I think, from the combinatorial point of view, the more intuitive relation. So this mobile has a recursive structure. So you have a root and then a series of mobiles that start with a black vertex, because it's bipartite. And in all of these black vertex, I have, of course, some degree. This comes, the degree of this comes from the number of white neighbors. So here I have two white descendants, and of course there is a third one up. And so I have to put three legs around, and there are several ways of putting these legs, and the number of ways I have to put here is just this binomial coefficient, and here I have r to the I minus 1 descendants. So the r, in this case I was 3, so I minus 1 is 2, and these are precisely again, so what I put here is just again such a bipartite model, so I get this kind of recursive relation. Okay, and I can rewrite it a little, and then I get that this representation is precisely the generating function of mobiles that are rooted by a white vertex, And by looking again at this relation, it follows that in the bipartite case, this is also precisely the same as the generating function of the rooted mobiles that are rooted at a black vertex. So if I take twice, I get just by the bijection from above, I get the rooted and pointed maps from this. So this is the lemma for bipartite rooted maps. So which is easy, and this was known, and it's a little bit more complicated if I want to consider the general version, where I consider not the bipartite situation. The difference is that here in the non-bipartite case, it's also possible to have black vertices, so that a black vertex in a mobile is related to is a neighbor of another black vertex. So we have to consider different kinds of mobiles when I want to count them. But finally, I get a system of equations. So it's again a recursive structure of these mobiles. So I have three different kinds of mobiles, and they are related by this equation. So of course, if I just go back to the bipartite case, this simplifies to the previous equation. And then I have again a relation of these mobiles to the generating function of maps. Okay, so this is, and here I get again all these variables. So it's at the moment it's just a formal power series in infinitely many variables. So it's the same idea, just a little bit more involved. But if I want to count maps where I have restriction on the degrees or on the phase valences, I can use this formal power series and do the following simple operation, that I put xi to 1 if I is in omega and xi to 0 if I is not in omega. And then this is just the counting generating function of those maps. This is a trivial thing. And so we can try to get out something in our case. So let's start with the bipartite case. So I have this generating function r, and now if I put all the xi's to 1, if they are in omega, and if I is in omega and 0 otherwise, I get now a relation for this generating function, and it will turn out that now this generating function has an analytic meaning. So this gives rise to an asymptotic analysis and will give the proof of the theorem. Well, this can be algebraically rephrased into this relation. And here omega is arbitrary, it's just a subset of the even positive integers. And so if this, for example, it is finite, this is just an algebraic equation, but if it's infinite, then it's a power series on the right-hand side. So, and we have to solve this. And there is I will call it folklore lemma, which goes back to Bender and many other authors, that if you have a relation of this kind, so this is a generating function, satisfies a functional equation of this kind, where the important property is that right-hand side, the coefficients are all non-negative. So there are no negative parts. So this is more or less a rephrasement of a combinatorial decomposition or a recursive decomposition. So if you have a generating function that satisfies an equation of this kind, then you usually get a Squareroot singularity. But where is this Squareroot singularity located? So in order to get this Squareroot singularity, you have to solve this system of equation. Of course, this Squareroot singularity plus the value of the function at the Squareroot singularity, which will be g of rho, this y0 will be g of rho, has to satisfy this equation. And there is a second condition which just says that the implicit function theorem, the condition for the implicit function theorem is violated. And if this is violated, you could expect a singularity, and actually under this condition, you will get a singularity of this kind. But it is very important that you get a solution inside the region of convergence of this function f. So if it's a polynomial, it's not a problem, but if it's a power series, you have to take care of that. And so we have taken care of the analytic properties of this right-hand side. But this is not that difficult. So let's make it very specific. So we have this functional equation. We have to solve this system here. This is just, it's just the same as this. And if you write it back, I get this thing here. And actually it turns out that we can formally eliminate the rho, which is because it only appears linearly, so we can eliminate, and we get an equation, just one equation for R0. Okay, and if we can solve it for R0, we can, if we have R0, we can just, from the second equation, we get back rho. Okay, and the nice thing is here that here we get equation for R0 which looks promising because the left-hand side is strictly increasing in R0, so it should hit 1 at some value, and this should be our solution. But we have to be careful that we are inside the region of convergence of this series. Again, if omega is fine, it's just a polynomial equation, so there is no problem. So let's stick on the infinite case. And the coefficient here has this kind of asymptotic. So you have 4 to the I times square root I times the constant. So this means if omega is infinite, then the right-hand side here of this power series has always the radius of convergence 1/4. You have 4 to the I times square root I. So it cannot be smaller, even if omega is a very sparse infinite set. So the radius of convergence is always 1/4. And we have the condition, because of this square root I, that this function goes to infinity as x goes to 1/4 from the left. So we can actually get a unique solution of this equation, which gives our R0. And this R0 is certainly smaller than 1/4, because if we approach 1/4 to the left, it goes to infinity because of this. We have infinitely many terms. So this solves the thing. So we can, this means we really get a solution inside the range of convergence. So we get a square root singularity in the bipartite case. So we get this square root singularity, and fortunately this method is very robust. We can also put some parameters, and we get also a square root singularity. And what we have to do is to integrate with respect to t. Therefore we have to put a t here, so we have integrate. And if we integrate the square root singularity, we get a singularity of this kind. And from this, it almost directly follows that you get this kind of asymptotics. So this proves the theorem 1 in the bipartite case, but this is not new because this was already proved by Bend and Canfield. So what you have to do in the general case is to consider this more involved system of equations. So now you have 3 equations, you can reduce them to 2, but anyway, and you have to show that everything goes through, so that you get a singularity of a square root singularity inside the region of convergence. These coefficients here are multinomials, so it's easy to deal with them, so you can deal with that, but it's a little bit more involved, and this gives you the proof of theorem 1. Concerning theorem 2, the same kind of philosophy applies. So the point is that if you have this random vector of random variables that count the number of this phase valency, phases of valency k, and you put it together into one possibly infinite vector, then in our setting, a continuous functional is just a linear combination of this, where Lk are it's related to this linear functional. And if we want to get the characteristic function of this random variable, it's just a product because of this linear sum. So you get a product, and if we translate this into the setting of generating function, it follows that if we put the characteristic function of the function of the distribution of the function of xn, then this generating function, of course, together with the number here, is just again the formal. At the moment is formal, the formal generating function of m, where I replace the variable xk by e to is lk. But lk is fixed. This is for every continuous function, this is fixed. So the only variable that remains, of course, I have to replace infinitely many of them. The only variable that remains is this s coming from the characteristic function here. So if I want to study distribution of this random variable, I again have to look at the behavior of this generating function m, where I have to replace the variables xk by these exponentials. Fortunately, the method I explained before are robust enough that you can get again a representation of this kind. The same kind of singularity. So of course you start with the mobiles, you get a corresponding equation for the mobiles, you get a squareroot singularity, then you integrate, you get this kind of singularity, and the only dependence, additional dependence, is this s here. So I get here some singularity that varies in s, but the kind of singularity is always the same. So by transfer method, reading of the coefficients, I get this asymptotic for the coefficient of this function. So the coefficient of this function is just this. So I get this representation for this. And I know the asymptotics of that, taking the ratio, I get this representation for the characteristic function of the distribution of any functionals, continuous function of xn. And you see here, it behaves almost like a power. And if it behaves almost like a power, then you immediately get that it satisfies a central limit theorem. So it's very direct to get a central limit theorem out of that. So if it were a precise power, it would be the sum of independent, identically distributed random variables. And here is almost an exact power, and by using Levy's theorem and a local expansion of this, around s equals 1, you get directly that you get directly a central limit theorem. So this proves the central limit theorem. Of course, there is a second part. We also need tightness. But this proves that all functionals, all continuous functionals, have a central limit theorem. And for tightness, so I don't want to go into details, but there is a theorem together with Gittenberg and Morgenbesser, where if you have a kind of equation where xk is a possible infinite vector of variables, and if you have some, and of course you can relate these variables to random variables xk. So where is it written? So you have x and k, so it's the random variable related to this. Then, and if you have some conditions on the derivatives of this function related at some special point, and then it follows that the random vector or the laws of this normalized random vector is actually tight. So I don't want to go into the details of this part of the proof, but you can you can prove tightness more or less by a moment condition, and so this proves, and under these conditions you get this moment condition, and we have to start with this kind of equation, and in our context, all these conditions are satisfied, so you also get the tightness and the Gaussian limit. Okay, so this is a short version of the ideas of the proof of theorem 2. I more or less stick to the bipartite case because it was easier to present. In the general case, everything is slightly more involved, also this tightness part. Okay, so finally, I want to consider also extension to Genus-y-Maps. This means that I consider a oriented two-dimensional manifold of genus G, for example, the torus of genus 1, and maps on this torus. And this kind of problem has also a long history, and I just mentioned the first result, where of Bend and Canfield, I think this was the first result, it was 1986, where they proved this kind of asymptotics for the number of maps with n edges on a surface of genus G, and you can see the kind of asymptotics. It's of the same form, exponential part, sub-exponential part that depends on the genus, and if genus G equals 0, then we get back minus 5/2, but for every genus we get an additional 5/2 in the exponent. And many things can be said about this coefficient here and so on and so forth. This is very recent work by Guillaume and many others. I don't go into the history now. But what I want to present to you is a notion that seems to be new. There have been special cases of that for quadrangulations and so on, but I think this is a general version, namely the notion of a genus G-mobile. So what is a G-mobile? This is a G-mobile. You have, for example, can you see it? So this is a torus. And what you are doing is the same as before. You consider a map on this torus with only one face. This is the correct generalization of a tree. And now it is a mobile. You have black and white vertices. You have these legs. So it looks almost the same as before. There's only one additional condition to make it a mobile. So what is the condition? So now you can have cycles on these mobiles. And on these cycles, you have to consider the number of white vertices. You have to consider the number of, in this case, you have 4 white vertices on this cycle. You have to consider on the left or the right-hand side of this cycle, so at once you have one side. For example, here inside you have 3 white vertices attached to this cycle to the left, and you have 1, 2, 3, 4, 5, 6, 7 legs into this direction. And there has to be a consistency relation, namely 3 plus 4 has to be 7. So the number of white vertices on the cycle plus the number of attached white vertices should be equal, or has to be equal, the number of legs going into this direction. So it's a slightly more complicated structure, but this is the notion of G-mobiles. You can, otherwise it's precisely the same. There are no white edges. The number of legs is again the number of white neighbors of a black vertex. You can define the degree in the same way. You can define a bipartite G-mobile where you have no black edges, and you can root it. Okay, and the nice thing is that these G-mobiles are in bijection to maps on a surface with genus G, pointed maps. And this is an extension of known results, but of Chapuis, Marcus and Schäfer, to the general situation. Maybe this has been done in parallel by other people, but we haven't seen this before in this general version, that this bijection for the genus 0 case extends to the general case in the same way as above. So you have white vertices correspond to vertices, black vertices to faces. The degree of the black vertice correspond to face valences. And bipartite case corresponds to the bipartite case, and also the rooted version, or the edge-rooted version, relates to the rooted version. So in order to count or to get some information on maps, you have to consider just G-mobiles. So what is the structure of G-mobiles? And this is something very well known, that if you have a structure like this, there is any G-mobile has a scheme on it. So what is the scheme? So the scheme, of course you see here many tree-like structures. If you remove all of them, and then what remains is a kind of skeleton or scheme that is uniquely given. And of course in the planar case you only have a single vertex that comes out of it. But on the torus, you see this can be more complicated. You have cycles here, and it's a nice thing that there are only finitely many different schemes on every manifold. So, but if now going back from the scheme, if you start with a scheme, you can construct all possible G-mobiles, of course. And what you have to do is you just put of course a series of vertices here and so on, and then to put some rooted mobiles on these vertices and so on and so forth. But you have to be very careful with this condition here, that the number of flags is not arbitrary, you put there. So this gives rise to some conditions. But anyway, and I will not go into the details now, but at least in the bipartite case, it's possible, well, to get a relation between the generating function of maps in genus G. Here you have again the derivative, which means that you go to the pointed version, to the generating function. This is more or less explicit in terms of the G-mobiles. And of course you have a sum over all possible schemes. For every scheme you have a generating function, and here you have some function S. So this looks very innocent, but this is a very important part here. What is the S? The S is more or less a series of cells. So you have a cell is a collection of a white and a black vertex. They are always alternating, put together. There's a cell, and the series of cells is a two-rooted mobile, and this generating function has to be put here. And here you get, so this condition, you have to be very careful with this condition. Here you get some increment. So the increment is put here in the exponent. So in order to get out this condition back, here you have to extract here this power, the coefficient of S, and this is not the power series but the Laurent series. But anyway, you have to put here the coefficient of the increment here of this power series, and so on and so forth. So anyway, you can do it, and after all, at least in the so-called bipartite case, which means that omega is only a subset of the positive even integers, we could get again the general version of the theorem. So we are more or less in the status of Bender and Canfield for G-mobiles and G-maps at the moment. So we can only get it for the bipartite case, that we again get, I'm sorry, this is strong. So this is wrong. This was copy and paste error. This should be, the genus should be here. Okay, you get universal asymptotics and also a central limit theorem. Thank you very much for your attention.
Thank you very much, Mr. for the very nice talk. Are there any questions? I'll try to do this in a moment.
So kind of obvious question from a probabilist's point of view, can you get larger deviation results? So you would replace the characteristic function by a Laplace transform and...
Yes. Yeah, for you can, yeah, yes, you can get it. So I go back to that. Well, of course, here you can, instead of is, you can consider a complex variable s, and so you can do it. But you get in this. So this means that you get some large deviation for every continuous functional. Well, this, of course, this is everything you can get, at least from my point of view. Yes, depends on the. You will get something in terms of the continuous functional. So will get some tail estimates related to the L star.
Yeah, so precisely regarding this slide, so so you're in the, say, planar, but then maybe not bipartite case. So you have for your mobiles probably a pair of equations, of implicit equations defining them,
yeah,
with all these LK parameters.
Yes.
And you want to apply a quasi-power theorem or something like that. And so, I mean, you've told us that it's the same as when you are just counting things, but you have all these parameters, so you have to locate and prove uniqueness of a singular position.
Yes. Yeah.
With a system of equations, and then they are not polynomials.
Yes.
And you need some uniformity to conclude to the limit law.
Yeah.
This must be horrible.
Well, of course, I'm hiding some things here.
Yeah.
But, well, going back to this procedure here, well, this lemma is very robust. So, well, here I have, if I can put a parameter here, and the point is that if this depends, say, continuously differentiable, and so on this parameter, and even if this parameter is a parameter in a Banach space, so then you can get through this, and you get the same kind of asymptotics, just here with some parameter. So you get here a parameter, here the parameter, and also the singularity depends on the parameter. So the point is that you can solve this equation here continuously in this parameter. If you can do this, then you are more or less done. That's the main point. So continuity in the parameter. So if you consider this equation, so of course, if you consider a parameter here and you want to solve this dependent on the parameter, it's again a kind of implicit function theorem. Okay, and you have to show that this works. But this is, if you have derivatives that are non-zero and so on, then it will work.
And the fact that you have a system of two equations, so you never get several candidates for the singularities, or? No.
The point is the non-positivity. So the positivity. So if everything is positive on the right-hand side, then it works smoothly. So then you can more or less eliminate, and you can trace it back to one equation. So this, I'm hiding things here. So if you can eliminate, and if in the strongly connected case, so if everything depends on each other, then you can put it back to one equation. That's the trick, more or less.
Thank you.
So yeah, another natural question from a probabilist point of view. It's more or less implicit. The covariance structure of the limiting Gaussian distribution is implicit in what you presented.
Yes,
can you write it in a simple form?
That depends on omega. Okay, but if to make it explicit, so if omega is the whole set, if you consider general maps, then you get you can explicitly get the covariance function. We did not make it explicit in the there is a paper, but this is just a journal version. One in the full version we will discuss it more precisely. But you can so what the thing is that you always have some implicit equation. So and depending on the solution of this implicit equation, you can write down more or less everything explicitly. So you get some covariance function in these terms. So you can say something also on how it will behave for large k and so on. So this you can get.
Thank you.
So if there's no more question, let's thank Michel again.